Okay, hello. We are beginning our derivatives unit. And so again, this is kind of like an introduction to calculus. This is going to be building off of previous ideas and, expanding on them, clarifying them, and continuing to develop our knowledge as we get into kind of some more calculus ideas. So one of the things that we need to talk about is a secant line. Okay, and a secant line works like this, where you touch your graph in two separate places. So a secant line only touches my graph twice. Whereas if I look at a tangent line, and I guess this function shouldn't have continuing on forever. If I look at a tangent line is only going to touch my graph one time. So if I were to think about right here, I would say this graph touches one time and that's it. So kind of in order to find secant, what you're looking for is you're looking for the slope of 2 points. And so we've talked a lot about slope, okay? Slope, growing up when you were younger, was described as rise over run. And then you might have described it as, hey, we can also talk about it as the change in y over the change in x. That's what this triangle means. Change in y over change in x. And then we said, well, how do you calculate it? Well, you take 2 points and you subtract them, and then you take the corresponding x values and you subtract them. And kind of how this gets shown in calculus is f of b minus f of a all over b minus a. Basically, all of these things are the same, the same type of idea. Whereas tangent, okay, so this is a tangent line. A tangent line only hits at one spot, only touches at one point. And so as our secant line moves closer and closer and closer and closer to zero, or to 1 point, as they get closer. Let's see if we can draw that. So again, here I'm getting closer. Here I'm getting closer. Here I'm getting closer. As we get closer and closer and closer and closer to this point, we call it the instantaneous rate of change. And we'll dig into that. So as we talk about this idea of slope, let's say that we take the function y equals 2x minus 1. As I look at this, I can absolutely calculate some specific points here. So let's say if x is 1, y is going to be 1. If x is 0, y is going to be negative 1. And if x is negative 1, y is going to be negative 2. So I can, draw this out. I can graph it. And I know that at every single point, this is a slope of 2. This is a slope of 2. Every single point on this line has a slope equal to 2. But if I compare that to maybe, say, a graph that looks like this, let's say something like this, I'm going to have slopes that vary throughout the whole thing. Let's call this point A. Call this point B. Let's call this point C. And then we will call this one more point, point D. So if I look at the slope of A, this looks like, if I kind of were to sketch it out, okay, I'm not sure what it is, but I know that it's going to be a positive slope. It's increasing. Whereas if I look at the slope of B, here, let's maybe draw our tangent lines slightly different. Again, that tends to be trending up. If I look at the slope of B, that tends to be more of a neutral, or if our graph levels out like that, there is no rise. If it's a horizontal line it has no rise over run. There's no rise, which means 0 divided by anything equals 0. So when we get these flat spots, these flat points, that means that our slope is going to be 0. Slope of C. If I look at here again, this is trending down, so this is going to be a negative slope. And slope D, again, maybe not as strong as slope of A, but still going to be a positive slope. So again, just looking at the different slopes in these types of intervals, it's going to be different than a linear function or a linear example. Now, like we've referenced up here, as our secant lines get closer and closer and closer to 0, eventually it gets to this point where they are the same point. It is the same point. And we call that the instantaneous rate of change. So finding all these different slopes, and that's again kind of this whole big topic of this new unit, is called the derivative. And the derivative is the slope of a tangent line. So again, like we looked right here, there could be multiple tangent lines that you're trying to find the slope of. But as this secant line gets closer and closer and closer and closer to 0, we call that the instantaneous rate of change. Which occurs at our tangent line. So some of the ways that you will see derivatives written is dy over dx. When you see this right here, that means find the derivative. Another way you may see it is f prime of x. That means find the derivative. And if it's not labeled as a function, it may be y prime. So again, these all mean to find the derivative, which means find the instantaneous change, rate of change, which is to find the tangent line. Let's say that we want to find the average rate of change. Again, what's the slope? You'll see this as AROC. So average rate of change of g of x equals x squared over the interval of -10 to 0. So again, you can see AROC, you can see you'll see it written a lot of different ways like we talked about here. I'm going to focus on the one that I'm going to use a lot in class is this one. So f of b minus f of a all over b minus a, where again we can call this a and this b in our interval. So what we're going to do is we are going to find the slope of the secant line. So again, my 2 points, I have point 1 and I have point 2. So the slope of my secant line, which is these 2 points. So if I just am writing in my equation, f of 0 minus f of -10 all over 0 minus -10. And I should probably do some side work. What is f of 0? What is f of -10? So again, my equation right here, g of x equals x squared. So if I plug in a 0, I'm going to get a 0. And if I plug in a -10, -10 squared is 100. So now I can easily plug in 0 minus -10 is +10. So this is going to equal -100 over 10, which equals -10. So my average rate of change from -10 to 0 is -10. Another example to find the average rate of change. of g of x equals negative 10x squared plus 13. And again, it's between x equals 0 and x equals h. And of course, h cannot equal 0. So again, using our formula, f of b minus f of a all over b minus a, to do some side work. So again, what are my a's and b's? I have 0 and I have h. I guess it technically should be a g because that's what my function is. G of h, g of x. All right, so if I plug in at 0, negative 10 to the 0 power plus 13 equals 13. And if I plug in at h, I get negative 10h plus 13. All right, so now I have some data that I can plug in. So f of b, or g of h minus g, my h's are terrible, minus g of 0 all over h minus 0. Negative 10h squared plus 13. Be careful because this negative would distribute. So if I had more than one term, I'd have to use parentheses. I don't. Over h minus 0. H minus 0 doesn't do anything, so I'm just going to leave it as h. 13 minus 13 cancels out. I have negative 10h squared over h, which means that my answer when h cancels out is just negative 10h. So the average rate of change of this interval of, 0 and h equals negative 10h. We have one more example to do, talking about instantaneous rate of change. Last example here. Instantaneous rate of change. Again, as those secant lines or points get closer and closer and closer to 0, we develop a tangent line. So I'm going to say that my formula is k of x equals negative 19, and I want to find that at x equals 5. So our formula that we use to find the instantaneous rate of change is we look at the limit as h approaches 0. We have f of a plus h minus f of a all over h. We've used this formula before. This is kind of like the derivative, and the instantaneous rate of change is the slope of tangent line. All right, so this is, our graph is just a linear function. Again, it equals negative 19 is a horizontal line. So since f of x takes on only one value, it never changes. So the instantaneous rate of change is going to be 0 because it's a horizontal line. So if I were to use this formula, again, what would I do? I would look at it, what my function, which is k of x equals negative 19 at x equals 5. So we would say, all right, the limit as h approaches 0 of k, every time I see my function, I'm going to take 5, because that's what my x is, plus h minus k of 5 all over h. Again, whatever my x is, because my graph is simply just, if this is negative 19, it's just a straight line. It's going to be pretty easy to plug in because my limit as h approaches 0, 5 plus h is just going to be negative 19, and k sub, or at 5, it's also negative 19 equals h minus a negative. So again, subtracting a negative cancels out. Negative 19 plus 19 cancels out. So we're left with 0 over h, which again, anything is going to equal 0. Anything divided by 0 equals h. So again, this was a kind of an easy one because our slope never changed. If you had a different function, again, all you'd have to do is find your values like this and then plug them in.